any given problem a complete sufficient statistics, then any function of that complete sufficient statistics, it is uniformly minimum variance unbiased estimator of its expectation. Now this greatly reduces the problem of finding out UMVUE for any parametric function as that of determining only a function of complete sufficient statistics which is unbiased for that parameter. I gave you a few examples, like in the normal distribution for the variance estimation, S square becomes UMVUE. Remember that we were not able to show using the method of lower bounds. Okay. Similarly, another thing that was there in the method of lower bounds, that only those parametric functions which are coming as expectations of linear functions of Sx theta, which is coming in the derivative, that is del by del theta product sigma log of fxi theta. The terms which are coming there, only UMVUE of that can be determined, because the lower bounds will be attained only for them. So in that way, this is a great shift, or you can say great jump in the method of proving or the obtaining the uniformly minimum variance unbiased estimators. So actually in today's and tomorrow's class, I will try to prove many results, or you can say derive the UMVUEs for various distributions. Of course, one or two additional concepts I will be giving you. I hope I have solved this problem. So let us consider this. So further examples, let me continue. I have given one or two as exercise also, so that also you should solve. So here we are considering the problem of finding minimum variance unbiased estimator for theta. Actually, I have considered unbiased estimation for this problem, consistency also. Now let us look at this one. Okay, so what is the complete sufficient statistics here? If you remember this is complete. It was minimal sufficient, so it is sufficient. Okay. And if you remember the distribution of this, that is ny to the power n minus 1 divided by theta to the power n. And expectation of y, that is n by n plus 1 theta. So this means expectation of n plus 1 by n y, that is equal to theta. So t, let me call it t1, that is n plus 1 by n y. This is UMVUE. You remember the method of moments estimator for this problem? What was the method of moment estimator? MLE was y, xn was the MLE, but the UMVUE is n plus 1 by ny. And the method of moments estimator was 2x bar. So if I am considering unbiased estimation, then I should use n plus 1 by ny, because this is the best among these. Okay. Is this application clear to you?
Yes, sir.
Not only that, I can pose a general problem. Okay. I am writing theta to the power k, where k can be 2, k can be 3 or anything. Okay. So this I am leaving as an unsolved problem, but I think you should be able to do it because you know the distribution of y here. So you can easily calculate the UMVUE of theta to the power k. I had given one problem, I think, in the last class. When we are considering a Poisson process, then the slack period, that means the period when there is no occurrence, that is considered to be of interest to people who are organizing this, say, service industry. So in the services, when there is no customer or there is no client or there is nobody to serve, then the period is considered as a slack period, and you can optimize your resources by employing less service facilities at that point of time. So estimation of the probability of 0 in Poisson distribution. So I'm making it simple rather than writing as a process. I'm just putting it as a Poisson distribution, and I am considering G lambda as probability of x is equal to 0, that is e to the power minus lambda. And I want the UMVUE of okay. So did anybody solve this problem?
Yes, sir.
Okay. So what is the method, or what is the answer first of all?
N minus 1 by n to the power summation xi.
N minus 1 by n to the power sigma xi. Okay. So how do you prove it? Let me call this as t. Then this is, say, h of t. Okay, where t is sigma xi. Yeah. How do you get this? Let us see that everybody else has understood it or not. Yeah.
So we consider an indicator function.
Okay.
Which will be 1 when suppose one of like x1 is 0, because we're finding probability of x1 is 0, and otherwise it will be 0, and then we'll find the probability that that indicator function is 1 when given that what is t is some constant s. Yeah.
Okay.
And then we go on solving that, and we obtain this result, n minus 1 by n to the power.
Has anybody else done this problem?
Yes, sir.
Okay, so I am not going to solve it. I think people have understood it. So this is UMVUE. Okay. Why this is UMVUE? Because this T, this is complete and sufficient. So if you apply the Rao-Blackwell-Lehman-Shafi theorem, you are calculating probability x1 is equal to 0 given t is equal to t. This should be calculated. Okay. So this is your HT, and as Rushil has told that this can be evaluated, it is turning out to be, basically you can say 1 minus 1 by n t to the power t. Okay. There is a actually significance of writing down like this. I will show you something interesting here. Okay, so what is the maximum likelihood estimator here for this problem? What is the maximum likelihood estimator for G lambda? So this is HT, it is the UMVUE. Okay. Let me call H1T as the MLE. What is the MLE of this? In this problem, you remember the MLE, maximum likelihood estimation? Does anybody remember the maximum likelihood estimator? So can you hear me?
Yes, sir.
Yes, sir.
Yeah, so what is the maximum likelihood estimator? The maximum likelihood estimator for lambda was x bar. So for e to the power minus lambda, it is e to the power minus x bar. Okay. See, this one I can write as this ht. I can write as 1 minus 1 by n x bar. So if I take limit of this as n tends to infinity, it will converge to this as n tends to infinity. So asymptotically, that means for large sample, MLE and UMVUE are same. So if you look at the previous exercise which I just now solved, n plus 1 by n y, that is the UMVUE. But as n tends to infinity, n plus 1 by n tends to 1. So this will converge to y, where y is the MLE. So asymptotic equivalence of UMVUE and MLE. So it was understood long back by some statisticians, and there are some research papers on this. In fact, in Annals of Statistics in 1973, there is a paper by the same title, Asymptotic Equivalence of MLE and UMVUE. Those who are interested, they can read this, okay? The author name is
Sir. Excuse me, sir.
yes.
So in this, the MLE was e to the power minus x bar. So if we were interested in the PDF of that distribution, how would we go about finding it?
That is not difficult because this is a PMF only. In the discrete case, so e to the power minus t by n, okay? So that is your h1t. The distribution of t is known to you. So this is simply a one-to-one function, isn't it? You know the distribution of t, that is Poisson n lambda. So what is the probability mass function? That is e to the power minus n lambda to the power t by t factorial. Okay. So this one you can write, this is simply a one-to-one function. I mean, like if I write s is equal to e to the power minus t by n, then log of s, then minus and n you put. So that is equal to t.
Okay, sir. Yeah, got it.
So I think you can just write down because this is a discrete case and it's a one-to-one transformation. So this is extremely simple. Okay.
So if suppose it was a normal distribution, t was a normal distribution, then how would we have proceeded?
We have already given the method for finding out the distribution of function of a continuous random variable. If you remember in your probability and statistics course, if x has a distribution, say fx, and y is a continuous function of that, of course continuous and differentiable, then we have proved two different theorems. One is that if it's a one-to-one function and it is increasing or decreasing, I mean if it is a one-to-one function, then either it is the g prime x is always positive or negative, then the density of y is obtained by fx g inverse y multiplied by mod of g inverse, I mean d by dy of g inverse y. And if it is a many-valued function, then in that case we find out the inverse images. That means you have G1 inverse Y, G2 inverse Y, GK inverse Y. Then you apply this on each of them, and I hope you need to revise this thing which is done in your probability course. I'm sure it must have been done there, isn't it?
Yes, sir. Now I remember. Yes, sir.
Yeah. Just you can revisit that thing. So that's not a problem. The distribution of function of random variable, that has been covered. Okay, before I move to other exercises, let me take up one or two related concepts also, because these are also related and also important. So now in completeness, what we are doing, in the completeness we are considering for any function, if expectation of gx is equal to 0, then gx must be 0 with the probability 1. Okay. Now we can put some sort of restriction on the definition. We can consider here, suppose it is true only for bounded functions, then what happens? Okay. So that is known as boundedly complete statistics. So let x be a random variable with probability distribution p theta, theta belonging to some parameter space script theta. We say that the family of distributions is boundedly complete. Expectation of gx is equal to 0 implies that probability of gx is equal to 0 is 1. So what is the difference from the complete family? That I have put this condition that if for bounded functions this implies, then it is said to be a boundedly complete family of distributions. So any complete family will be boundedly complete. Completeness implies bounded. However, the converse is not true. So I will give you one example where the family is boundedly complete but not complete. I will construct a discrete distribution and probability mass function is given by 1 minus theta square theta to the power x for x equal to 0, 1, 2 and so on, and probability of x is equal to 1, that is x equal to minus 1, that is equal to theta. So you can consider it as a extended geometric distribution. If you remember the geometric distribution, it is 1 minus theta into theta to the power x, or theta to the power 1 minus theta. I mean, one can write theta or 1 minus theta interchangeably also. So we have considered different forms of that. Or we write it as 1 minus theta into theta to the power x minus 1, etc. So what here we have done, we have shifted it. That means we have added a point x equal to minus 1 here. Okay. And here, of course, theta lies between 0 and 1. So let me consider here expectation of some hx is equal to 0. So let us write it, because the distribution of x is known to me. So this condition is same as saying sigma hx into you have to write down this probability mass function. Okay. So h of minus 1, this is equal to theta plus sigma h of x 1 minus theta square into theta to the power x, x equal to 0 to infinity, that is equal to 0 for all 0 less than theta less than 1. So we write it slightly differently. See, this term I write on the left hand side and this I take to the right hand side, and you can divide by 1 minus theta square. So the term you will get in this particular fashion, hx into theta to the power x, x is equal to 0 to infinity, that is equal to h of minus 1. Of course, minus will come because we are taking to the other side, divided by 1 minus theta square. And here theta is between 0 and 1. The right hand side is 1 by 1 minus theta square. I can consider Maclaurin series expansion, because theta lies between 0 to 1. So this is minus h of minus 1 theta, and this becomes 1 plus 2 theta plus 3 theta square and so on. I think all of you know this kind of terms. So now the left hand and the right hand both are the power series in theta. So the two power series agree on an interval if and only if all the coefficients agree. Okay. Two power series are identical on an interval if and only if all the coefficients match. So this implies that h of x is equal to, so what are the type of terms you are getting? First one is 1, second one is minus, I mean minus is of course there, 2, then the third one and so on. So it is basically coming like this, minus x h of minus 1. Because this theta is coming outside, so theta square, theta cube and so on it will come. So we have got a general solution of hx, and all the terms are actually multiples of h of minus 1. So if h of minus 1, I mean, if you say that this function is bounded, then the only way this can be bounded is when h of minus 1 is 0. If h of minus 1 is not 0, then hx will become unbounded because it is multiplied by x. So as x increases, it will keep on increasing. So if hx is bounded, then h of minus 1 is 0. And in that case, because it is multiple of h of minus 1, so hx is 0 for all x. This means that the probability that h of x is 0 is 1 for all theta. So the family is this family of distributions is boundedly complete. However, if I take h of minus 1 to be non-zero, then hx will not be 0 for any value except, of course, for x is equal to 0. That's all. For no other value, this will be 0. If h of minus 1 is not 0, then hx is not 0 for all x not equal to 0. So probability of hx is equal to 0 will be less than 1. So the family is not complete. That means for any function, if I take expectation of hx is equal to 0, then it does not imply that the probability of hx is equal to 0 is 1. So a boundedly complete family need not be complete. Okay, so is the concept and the this example clear to all of you?
Yes, sir.
I will state another theorem, which is again of particular significance, but I am not going to write the proof of this because these proofs are involving certain major theoretic concepts. So if Tx is complete and sufficient, then Tx is minimal sufficient. Once again, the converse is not true. That means a statistic may be minimal sufficient but not complete. But the examples for that we have already provided, like if we are considering two normal distributions with a common mean mu, I have shown you that minimal sufficient statistic there, that is x bar, y bar, x square, sy square, it is not complete. I also considered examples like normal theta, theta square, etc. And there also the same thing you observed. Okay. Now I will come to another concept, which is again very much related, but it has deep significance. It is called the concept of ancillarity. That means if the distribution of a function of random variable does not involve parameters of that distribution. then it is said to be ancillary. So if the distribution of a statistic does not depend upon a parameter, then it is said to be ancillary statistic. Okay. Let me give some examples here. So let x1, x2 follow normal mu1. Okay. And suppose they are independent and identically distributed, normal mu1, where mu belongs to R. Okay. Let me consider, say, y is equal to x1 minus x2. Then what is the distribution of y? That is normal 0, 2. This is free from mu. So here x1 minus x2 is ancillary. Let us take another example. Suppose I consider x1, x2, xn following normal mu sigma square. Okay. And I consider this s square, that is 1 by n minus 1 sigma xi minus x bar whole square. Then the distribution of n minus 1 s square by sigma square, that is chi square n minus 1. That means it does not involve mu. So the distribution of s square involves sigma square only. The distribution of s square involves sigma square, but not mu. So here s square is ancillary for mu. Okay. It is not ancillary for sigma square. So I hope this concept is understandable.
Yes, sir.
Now we have one important result. It is named after Debabrat Basu actually. In 1955 it came. But because of its significance, it has become synonym with his name. He was actually the first PhD student of C.R. Rao. So let me write the full description of the model. So let x1, x2, xn be a random sample let Tx be sufficient and boundedly complete. Let V be ancillary for theta. Then Tx and Vx, they are independently distributed. So basically what we are saying is that ancillary statistics are independently distributed of complete sufficient statistics. Here I have stated the result for boundedly complete, but since complete statistics are also boundedly complete, therefore the result will be true for them also. Okay, so let us consider, let A be any set of values of Vx. Okay, Vx takes values in some space, and let A be any set there. So we have to actually prove that if I have to show that the V is having a distribution independent of theta, so that is given to us. So I have to make use of that. That means we must use this information that probability of Vx belonging to A, this will be free from theta. If it is free from theta, then this is some constant. That is, there exists some alpha in the interval 0 to 1 such that p theta Vx belonging to A, that is equal to alpha. Now let me consider conditional probability here. So let me put this as probability of Vx belonging to A given T. This is a probability and it is a bounded function. The conditional distribution of x given T is independent of theta because T is a sufficient statistic. Okay, so this is merely a function of T. W is a bounded function because it is probability, so it lies between 0 to 1. Bounded function of T only. Okay, now let me consider expectation of Wt minus alpha. So this is equal to expectation of Wt is probability Vx belonging to A given T minus alpha. So this is expectation of the conditional probability. So this simply becomes probability of Vx belonging to A, which is equal to 0. Now here Wt is a bounded function, so Wt minus alpha is a bounded function. I am saying expectation of this is 0 for all theta. Since Wt minus alpha is a bounded function of t. Let me call this equation as, say, 1. Equation 1 implies that probability that Wt is equal to alpha must be 1 for all theta. But what is Wt? Wt is nothing but probability of Vx belonging to a given t. That is probability of Vx belonging to a given t is equal to alpha, that is Vx belonging to a, with probability 1 for all theta. Here actually this part need not be written. Why? Because if you look at Vx belonging to a given t, conditional distribution of x given t is independent of theta. So actually this is free from theta. And if V is ancillary, so the probability of V belonging to something, that is also free from theta. So this can be basically removed from here in this statement. Okay. So I wrote it here just for consideration here, but now you can consider that it is of not much use here. So then this is equal to this with probability 1. That means the conditional probability distribution of V given t is same as unconditional distribution of V, because A was any arbitrary set here. So V and T are independently distributed. They are independently distributed. Let me repeat the proof here. So what is the statement of Basu's theorem? In a given problem, I have a sufficient and boundedly complete statistic, and there is another ancillary statistic. Then the Basu's theorem says that T and V are independently distributed. In order to prove that, I will prove that the conditional probability of V given T for any set is same as unconditional probability of V belonging to that set. So I take an arbitrary set A in the space of values of V, and since V is ancillary, then probability of Vx belonging to A is free from theta. That means it is equal to some constant for all theta. So I am calling that constant as equal to alpha. Next, I define conditional probability distribution of V given T over the set A. I call this function as Wt. Obviously, since the conditional distribution of x given t is free from theta because t is sufficient statistic, therefore this is a statistic. That means it's a function of t alone. And this is probability, therefore it lies between 0 and 1. Therefore w is a bounded function. So now I consider expectation of Wt minus alpha. So expectation of the conditional probability becomes unconditional probability minus alpha. So this is equal to 0 because that is what we have assumed here. Now Wt minus alpha is a bounded function. Therefore, expectation being equal to 0 implies that the function is 0 with probability 1. That means W2 is equal to alpha with probability 1. But W2 is nothing but the conditional probability and alpha is nothing but the unconditional probability. Now these terms are free from theta because here it is conditional distribution of x given t coming into picture. So since t is sufficient statistic, this is not involving theta. Here V is ancillary, therefore anyway theta will not appear here. So this thing I can remove here, and here I can forget about theta. So I am getting the conditional probability of V given t is unconditional probability of V for every set in the space of values of V. So therefore V and T are independently distributed. Okay, so is the proof clear?
Yes, sir.
Now, this theorem, it has a lot of potential actually, because in most of the inference problems, we deal with several statistics, especially in the estimation and testing, and then we need the joint distributions and various kind of things. So usually things become quite complicated. Okay. So this Basu's theorem actually is helpful to derive many distributions because of the independence structure. Okay. So let me just give one or two examples here.
Sir, you are not audible.
Yeah. Just I'm just checking one reference actually. I'll just give you. Is the screen visible?
Yes, sir.
So I am writing one reference here because I think those who are interested in little bit of more historical things as well as the new perspectives, you should read something. Okay. It is not that only I will teach lot of examples here. You should also see this. So Basu's theorem with applications. This paper is by Malay Ghosh, and it has appeared in the journal Sankhya 2002 volume 4, volume 64. Now it is available through our library website because Sankhya has been taken over by Springer, etc. So this journal you can download and read it actually. So this will give you a lot of insight into the significance of this work. Okay. So that is why I just wanted to show you this one. Okay, let me start with some examples here which I was going to discuss. So let us take, say, a random sample from normal distribution with mean mu and variance sigma square. So suppose I take sigma square is equal to sigma naught square, some fixed value. Okay. In that case, you already know we have already solved this problem several times. So this is sufficient, and of course it is complete. And if I consider this sigma xi minus x bar square, this is ancillary for mu, because the distribution of n minus 1 s square by sigma square is chi square on n minus 1 degrees of freedom. So this is ancillary for this. Okay. So x bar and sigma xi minus x bar square, they are statistically independent. Okay. Now, if you look at this statement carefully, I said let sigma square is equal to sigma naught square be known. Okay. So now if it is known and I keep on changing the values here, okay, then for every sigma square is equal to sigma naught square, same statement will be true. Therefore, because here the distribution of sigma xi minus x bar square, it will not involve mu, whatever be the mu, okay, and whatever be sigma square. So since sigma naught square is fixed arbitrarily, we conclude that x bar and sigma xi minus x bar square is they are independent. Okay. Let us look at another variation of this. Okay. Let us take mu is equal to mu naught to be fixed. If this is fixed, then W is equal to say sigma xi minus mu naught square is complete and sufficient. I am giving some statements here, but each of these requires some proof kind of thing. In normal mu sigma square, if mu is equal to mu naught is fixed, okay, then sigma xi minus mu naught square is complete and sufficient. How many of you agree with this statement? And you can say that you know the proof of it. If I ask you to prove it, can you tell me the proof immediately? Rushil?
Sir, I need to work it out, but after
So
that,
if you consider the joint distribution, that is 1 by root 2 pi to the power n sigma to the power n e to the power minus 1 by 2 sigma square sigma xi minus mu naught square, isn't it? So in this case, see, if I am taking this to be fixed, then the joint PDF of x1, x2, xn is, now mu is known, so I don't have to write it here, I'll just forget it here. And this is sigma square, that is 1 by root 2 pi, okay, to the power n, sigma to the power n, e to the power minus 1 by 2 sigma square, sigma xi minus mu naught square. So this is actually one parameter exponential family. This is coming here. The range of sigma square is positive. So it contains one dimensional rectangle or interval. So this T, it will be complete as well as sufficient. Sufficiency follows from the factorization theorem. Completeness follows from the structure of the distribution here. That means it is one parameter exponential family. So the parameter multiplied by the statistic here. Is that clear? So from here it follows that this is complete and sufficient.
Sir, can you repeat?
So I have written it as a one parameter exponential family here. So this is say theta, this is Tx, this this is your Hx, and this is say Hx, and we write something, no, some g theta kind of thing, or yeah, and then e to the power theta Tx. Is it okay?
Yes.
So by factorization theorem, T is sufficient, and since it's one parameter exponential family, the parameter space contains one dimensional intervals, therefore T is complete also. So completeness and sufficiency follows. Now I consider another statistic, say V, okay, and it is defined as say x bar minus mu naught divided by square root sigma xi minus mu naught. square. Okay. So if you consider, see, what are the, suppose I consider the distribution of xi minus mu naught by sigma, that is normal 0, 1, isn't it? So they are free from parameter here, and here x bar minus mu naught root n by sigma, that also follows normal 0, 1. So this is also free from parameters. So V, distribution of V does not depend on sigma square. So W and V are independently distributed by Basu's theorem. Okay, so I hope the example is clear to you.
Yes, sir.
But here I will not give the argument which I gave just now, that if I change mu, then what happens? Because that statement will not be true, because this statistic is dependent upon mu. Okay, so I cannot say that this is independent of that without mu. So that statement I will not give, which I gave just in the previous case. Okay, but this statement is okay. So let us continue. Now let us summarize. Actually, now onwards I will actually look at some of the problems and various kind of applications. What are the things that are now important? So in a general inference problem, okay, we look at sufficient statistic, we look at minimal sufficient statistics, we look at complete statistic, we look at some ancillary statistics, this, then we consider, say, maximum likelihood estimators, we consider method of moments estimators, we consider UMVUEs, then of course unbiasedness and consistency also remains there, because this UMV will include this thing. So I give you a mega project here, okay. So if I consider normal mu sigma square, then I will consider several models like normal mu1, normal 0 sigma square, normal mu naught sigma square, okay, and of course normal mu sigma square. Suppose I consider, say, exponential, okay. Then again I will have several models like exponential lambda, exponential mu, exponential mu lambda, okay. Similarly, say double exponential and so on, okay. So I'm not listing all of them, gamma, Poisson, etc. So you write as many as possible. MSEs mean mean squared errors. Okay. So this is a mega exercise to all of you, and I will expect this to be submitted in another 2 weeks time, okay. So today is 17th, so maybe by just maybe put let me put, say, by 5th of March or something like that, okay. Or maybe I'll give 2 more days, maybe 7th March you submit, okay. You will have to submit the PDF files, okay. I will give you the link where you have to submit all of them, okay.
Yes, sir.
Okay, so I will now spend remaining time today and tomorrow for various kind of problems, okay. I think I saw in the MS team somebody has written the exam date as 25th. So is it okay to all of you, 25th?
Yes, sir.
Yes, sir.
Okay, so the exam is going to be little longer. I will give you maybe 3 hours time. Shall we keep it something like 7 to 10 or 6 to 9 kind of thing?
So 6 to,
Yes.
So
6 to
during
9.
class hours?
2 to 4. Will you be able to complete in class hours? Because you have seen all the exercises are lengthy. If I
No, sir. 2 to 5 something.
2 to 5,
5,
you
okay.
can keep.
Yes, sir.
Okay, 2 to 5 is fine. If all of you agree, then it's fine. Okay.
Sir, and what is the platform?
Yeah, so you have to solve the problems, scan them, convert it to PDF file and submit it. And I will give you a separate email account where you have to submit, because don't send on my regular email, otherwise my mail will be flooded. I mean, this will become jam. So I will give you another email ID where you have to submit. Okay. Because this is going to be lengthy. I cannot ask objective type questions like we asked in the probability and statistics courses. Okay. So this is a lot of theory. So just asking simple objective type of questions is not going to work here. So the questions will be long. I mean, like each question may take 15-20 minutes. So I have to, even if I give you say maybe 10 questions, then it will take more than 3 hours. So you have to solve them nicely on your sheets, on white sheets, and scan this and submit it to me. Okay. Is the method clear to all of you?
Yes, sir.
Actually, the way of teaching has been that I have been solving enormous number of problems. Actually, with every concept, I solve 10 problems. So that is why I have not given any separate assignments. It is not required. And if you do this mega project that I am giving to you, then probably you will be clear with everything. Okay. So because all the problems will be related to some of the standard distributions only. It is not that I will invent some distribution and give some problem. Okay. So if you are familiar with all the standard distributions and the working out of that, then you should be able to solve problems which are related to that. Okay. So it will not be standard problem coming from the book which I have already solved, but something related to that. So maybe little variation in the estimator, or in place of the given parameter, I change the name of the parameter and do something. So I think this all you should be able to do. Okay, so I think this is fine. The method of class test, everything is clear to all of you.
Sir, how many questions can we expect?
The one which you can answer, that's all. Exactly, I cannot tell right now, but maybe 5 to 10 questions. Okay. 3 hours you have, so the question paper will be of length in which you can answer in 3 hours. Okay. All right. And I will give you some weightage, sufficient weightage for the mega project that I have given you. Okay. So that also you please submit. Shall I proceed? If you have no other questions, then I will proceed further with exercises.
Yes, sir.
So suppose X has a hypergeometric distribution. I mean, whatever problems I am doing, these are basically, you can consider this as assignment only. Okay. So all of you are familiar with this. Okay. This hypergeometric, all of you have done. What does it represent actually? This X, what does it represent? What is capital N? What is capital M? What is the small n? Because a statistical inference problem relates to a real situation. So it is not that some mathematical function I am just writing and asking some exercise. So what is the statistical situation here for which this kind of probability mass function is coming? Can you tell me? Anybody? Let me ask somebody from the existing list. Vismay Parija. Vismay Parija. Shri Ram. What is the physical situation in which this distribution arises? What is capital N? What is capital M? What is small n? And what is X? Venkat Sai?
Sir, no ideas.
Have you not done a hypergeometric distribution in your probability course?
Yes, sir, but sure.
But you are not remembering. Yeah, so inference course is a second course actually. So it is understood that the probability concepts must be very clear to all of you. Otherwise, I mean, this is just like some mathematical theory I am teaching, but it is actually practical. So unless you remember the things. So here capital N is the population size. Capital M is the number of items of type 1 and N minus M is the number of items of type 2. Hello. And from this population, if I take a random sample of size small n, then it will contain some items of type 1 and some items of type 2. So capital X denotes the number of items of type 1. So it is the probability distribution of that. I mean, so it's like this. So the class has boys and girls. So if I take a random sample of size, say 5 from this class, then how many boys are there? If I look at the distribution of that, then that is hypergeometric distribution. So if I consider a population, I mean, say students in the hostels, and so some of them are there, those who have got COVID earlier and those who have never got COVID. So if I take a random sample of the students from the hostels, and if I look at X as the number of students who were affected with COVID at some point of time, then the distribution of that will be hypergeometric. So I hope it is clear to all of you.
Yes, sir.
Here we can have different situations. That means the M may be unknown. So for example, I don't know how many of you got affected by COVID, and I want to estimate that. So from the sampled students, I look at, and so X is known to you. Then on the basis of the total population size, we want to estimate M. That can be one problem. Another problem could be estimation of the population size that we have already given example in the probability course, like capture, recapture technique, etc. So based on something, the total population size, that means suppose we are there are people who have been COVID infected but not tested, and those who have been infected and tested. So these are the things. So suppose I want to look at total population size of the COVID infected people, then maybe N is unknown. So there can be different inference situations. So let me consider, suppose N is known Let n be known. And we consider the estimation of m. So basically this x is a summarized statistic because we took a sample of size small n. Out of that, capital X is the number of people who are number of items of type 1, isn't it? So on the basis of that, we want to consider estimation of m here. Okay. So let us consider from the form of the distribution, what is a sufficient statistic or what is a minimal sufficient statistic? Now, from the form of distribution, what is a sufficient statistics here? Yeah. If you have understood the concept of factorization, the minimal sufficiency, then you should be able to answer these questions. I expect the answers from the students. Jay Kumar Thakur. Mukesh. Shashank. Swaroop Padhi. Priyanshi. I think most of the students, they are just switched on. They are looking at the recording only. They are not answering the questions. So if you look at the factorization theorem, X is basically sufficient and it can be proved to be minimal sufficient also. Because that is the summary of the data of the number of people who are of type 1 in the sample of size is small n. We will try to prove that let us take, say, expectation of gx is equal to 0. Okay. So this means sigma gx mcx n minus mc n minus x divided by ncn for x equal to 0 to n, that is okay for all n. Now here you see I can actually remove this NCN. I can remove because this is non-negative. I can just cancel it out. So you are left with gx into this factorials here. I mean, basically combinations that is coming in the form mcx and n minus mc n minus x. So since I am saying it is true for every m, if I take, say, m is equal to 0, then if I take m is equal to 0, then this term vanishes, NCN cancels out, so you get G0 is 0. Now if I take, say, m is equal to 1, then I can write here G0 n minus 1 C n plus G1 n minus 1 C n minus 1, that is 0. If G0 is 1, then this will imply that G1 is also 0. So by induction, I can show that Gx is equal to 0 for x equal to 0, 1 to n. Okay. So this means that probability that Gx is equal to 0, that is 1 for all n. So x is also complete. So it is minimal, sufficient, and complete. Is the proof clear?
Yes.
So if I consider expectation of x, then you know here the expectation x is n by n into m. So if I take this to this left hand side, that is equal to m. So you have got the UMVUE. So I am giving alternative problem here that suppose m is known and n is unknown, then find out the UMVUE of n. Okay. Actually, this has more importance in the case when the populations are very large and they are unknown due to hidden characteristics. For example, if I want to find out how many people are HIV positive in a population, okay, so obviously HIV positive will not be clear because the onset of the disease from the infection, it takes long incubation period. Some people may not get affected in 5 years or 2 years or 10 years, but they may be HIV positive. So if I want to find out the incidence of that, then how to do that? So that becomes more difficult problem, and one can look at such kind of things. Let me take another non-conventional distribution. Yeah.
So here the hypergeometric distribution has capital M and capital N as the parameters, right?
Capital M and capital N, but in different situations, different things will be known and unknown. So here I have solved the problem where capital N, that is the total population size, is known, but the number of type of people which are type 1, that is unknown. So in order to estimate that, we have constructed an UMVUE here. But you can have the different situation where capital N, that is the total population size, may be unknown, but the number of people who are selected, I mean, like one type of people, that may be known. Okay, so that is a different kind of situation.
And it wouldn't make sense to vary small n, right? That is not a parameter, is it?
Small n is the sample size. That means we take a sample of size small n, so that is known to us.
Okay, yeah. Yes, sir.
So I have a binomial k theta distribution. K is known. Okay, and theta, of course, lies between 0 and 1. In binomial distribution, one of the parameters of interest is a single occurrence or the probability of a single occurrence. So here if I consider that is equal to k c1 theta 1 minus theta to the power k minus 1. Okay. We are interested in estimating the probability of 1. Like I mentioned in the Poisson distribution, estimation of 0 or the occurrence of 0 or the probability of occurrence of 0, that is important. However, in binomial distribution, many times single success is considered to be very, very significant in the sense that it leads to the possibility that there is a solution to a given problem. For example, when the first compound is discovered for the COVID vaccine, okay, so then they become hopeful that okay, this can work, and then they go for further trials. So same thing happens with the development of the different kind of medicines for different kind of diseases. So some component or some compound or some chemical reaction, it is found to be effective on some organism, and as soon as they observe some success, then they start trials for various things. So probability of one success, that is important in the binomial or Bernoulli situation. So suppose we are considering this. Okay, so what is a complete sufficient statistic? I will not derive it here. I think you can easily understand. So sigma xi will be complete and sufficient. So I construct this indicator function here. Then expectation of hx1 is equal to g theta. So to find UMVUE, it is conditional expectation of hx1 given t. So the challenge is to calculate this conditional expectation. Fortunately, because these are we are dealing with the discrete distribution, this can be actually calculated. So let me show you the calculation. Although for Poisson, some students have already done it. So similar kind of thing you can do here also. So conditional probability is the joint probability divided by the okay. So some of the binomials is again binomial because here p is common. So this t follows binomial nk theta. And this we can write as probability of x1 is equal to 1, sigma xi I is equal to 2 to n is equal to t minus 1. The last one I am subtracting here, and in the denominator probability sigma xi I is equal to 1 to n is equal to t. X1 and this x2 they are independent, so I can write it as product of the probabilities. So this sigma xi I is equal to 2 to n, that will follow binomial n minus 1 k theta. So that is equal to probability of x1 is equal to 1, probability of sigma xi I is equal to 2 to n is equal to t minus 1. So now using binomial distribution, we can write all these probabilities here. So the first one is probability x1 is equal to 1. That is nothing but k theta 1 minus theta to the power k minus 1. And then you have this is binomial kn minus 1. So kn minus 1 c t minus 1 theta to the power t minus 1 1 minus theta to the power kn minus 1 minus t plus 1. And in the denominator it is kn t theta to the power t 1 minus theta to the power kn minus t. So these theta terms will get cancelled out, and you are left with k into n minus 1 factorial into kt into kn minus 1 kn minus t factorial divided by kn factorial kn minus t minus k plus 1 factorial. Okay, so this is a function of t. Now this is a function of t here coming. T is coming. So this is a little complicated, but anyway, we have got the minimum variance unbiased estimator here. Okay, is the argument clear?
Yes, sir.
Okay, anybody solved the exponential distribution problem which I gave last time? The estimation of reliability function.
So it was coming as a complicated expression, so I'm not sure if I did it correctly. Should it be a large expression or?
Large, but ultimately it reduces little bit. I mean, there is some simplification there. Okay, so maybe I can show the calculation. So suppose I have a random sample from exponential distribution with parameter lambda. So what is the reliability function? That is the probability of x1 greater than t. That is e to the power minus lambda t. So you are all familiar with the reliability function of the in general, that is probability of x greater than t, that is called the reliability function. So in general, I am looking at the exponential distribution problem here, and what is UMVUE for this? So we look at indicator function of this, that is 0, sorry, this is equal to 1 if x1 is greater than t, and it is 0 if x1 is less than or equal to t. So here expectation of gx1 is equal to RT. In the exponential distribution, the joint so by factorization theorem, sigma xi is sufficient, and by the exponential family thing, sigma xi is also complete. So sigma xi is complete as well as sufficient. Can anybody tell me what is the distribution of t?
Sir, gamma n comma lambda.
T follows gamma n lambda. Here what is required? If I want to apply the Rao-Blackwell-Lehmann-Shafi theorem, then the conditional distribution of x1 given t will be used here. Okay. So by Rao-Blackwell-Lehmann-Shafi theorem, So let me call it, say, h of t, that is expectation of this g of x1 given t is UMVUE. Remember here that this is not a discrete distribution. So the kind of statement which I gave just now, you cannot write like this. This kind of statement we will not be able to write. Okay, that probability x1 is equal to 1 given sigma xi is equal to t. Because this is continuous distribution. So continuous distribution, the probability of a point is 0. So you have to actually evaluate it. Okay, that means this is nothing but probability of x1 greater than t given t. Okay, so this is your ht, and we have to actually calculate this. That means the conditional distribution of x given t, that has to be calculated. Okay, so can anybody suggest me now that how this will be calculated? Okay, in place of t, let us put something different, because t is also coming in RT. So there is a little bit notational confusion. We can change this here. Okay, I will call it yeah, I'll give a different name here. We can call it y here. Because this t is coming here also, so we should not confuse with that. Okay, so conditional distribution of x given sigma xi. Can anybody suggest me how it will be obtained? So you can obtain it in the following way. The conditional distribution of x1 given y can be obtained by writing down the joint PDF of independent random variables x1 and I will call it, say, w is equal to sigma xi, I is equal to 2 to n. See, this follows gamma n minus 1 lambda, because this is involving x2, x3, xn and x1 here. So x1 and w will be independent. The distribution of x1 is known, the distribution of w is known. So you can write down the joint distribution of x1 and w. Now what is y? Y is x1 plus w. So you make a one-to-one transformation from there to find the distribution of x1 and y. And once you have the joint distribution of x1 and y, you can find the marginal distribution of y, which is of course anyway known because it is simply gamma distribution, and then you take the ratio. So immediately you get the conditional distribution of x1 given y. So let me write it here. Okay, is the procedure clear to all of you what I mentioned? N minus 1, 1 minus, okay, or maybe I'll put it as one term, not as y minus x1 to the power n minus 2 divided by y to the power n minus 1 for 0 less than x1 less than y. And it is equal to 0 otherwise. Okay, did you understand the procedure? I mean, this part I am leaving as exercise to be solved. Of course, it is not very difficult because I have already explained the methodology. Okay. Did you understand the procedure? How will you obtain the conditional distribution of x1 given capital Y?
Yes, sir.
Okay. So this I am leaving as an exercise. So now once you have this distribution, you have to just calculate the conditional probability. X1 given t greater than t given y is equal to y. That is obtained just by integrating this. Okay, you have to just integrate this, and of course you have to remember here x1 is greater than t, so t cannot go beyond this one, so it will become 1 minus minimum of y and t divided by y to the power n minus 1. So 1 minus minimum of y t by y whole to the power n minus 1 is UMVUE of the reliability function. So this is giving a solution to the estimation of the reliability function in an exponential distribution. Actually, these are all research problems, and I am only giving the beginning of the research problem. So for example, if I consider several exponential distributions, or if I consider 2-parameter exponential distributions, and then if I have several exponential distributions, then there can be some restrictions on the parameter spaces. So in different situations, what are the estimates of the reliability function? So these are all important research problems. Many statisticians have worked on this. Even my research scholars, we have published some papers on this. So this is the beginning, and if the concept is clear, only thing is that for different models, because generally what happens that I mean, it is not like just a mathematical thing that I take in place of 1 exponential, I take 2 exponential or 10 exponential. Generally, the problem arises from the field data. So in the field, you have different kind of situations. So suppose the data is on the lifetimes of certain components, and you have several sets of components or equipments. Then each of them may follow different exponential distributions. And now I'm looking at, say, combined reliability of the system, or suppose it is a series system, or suppose it's a parallel system. So for the complex system, the distribution may become a little bit complicated, although each component may be exponential, etc. And then find out the MLEs, the unbiased estimators, UMVUEs for those problems. So these are become research problems because of the applications to the real life situations. Okay. So maybe I think I will stop today's class at this point. In tomorrow's class, we will devote to various problems on all the concepts that we have done so far, so that you are ready for the exam. And once again, I think some student wrote a comment on the MS Teams that I should give some problem sheets or some tutorial sheets. So it is not a first year class or some sort of school class. Whatever I am doing, for everything I am giving a lot of applications. So these are the tutorials basically, and you need to solve many more actually based on this. Okay, so this is little bit advanced. So don't expect tutorial problems of the kind that we give, like find out solution of a differential equation or find out probability of something. It is not like that. I mean, these are all concepts, and based on that you have so many applications. So I think you should do that. Okay, and I have given you a mega project which involves all of them. Okay, so I will stop today's class at this point. Do you have any questions? Anybody is having any doubt? I have already given the date and time of the exam, the type of exam that will be there. Okay, so exam is on what is that, 25th of February. 2 to 5, and it is subjective type. Okay. And your project due date is 7th March, and I will give substantial weightage to that also. Okay, so if you have no questions, I will stop today's class.